Mind-blowing new images today from the LSST camera on the Vera Rubin Observatory in Chile. This amazing new camera, the largest astronomical camera ever built at 3.2 gigapixels, is still in the commissioning and testing phases, but the team held a press conference today where they showed off some incredible views of the universe. Here are the Trifid and Lagoon nebulas in a 24 gigabyte image from 678 exposures from the camera. It's important to note that the 678 exposures are stacked to reduce noise and improve the details, but this is not a mosaic. The actual image only represents a fraction of one field of the LSST camera, and it captures one of those large fields roughly every 30 seconds. Here you can see the full moon superimposed on the camera sensor to get an idea of how much of the sky Rubin is capturing with each image. The incredible details that come out when you zoom in on these images are truly awe-inspiring. An online tool is available for looking at the data, and if you head to skyviewer.app and use the Explore option, you can zoom in and around Rubin images for yourself. This image, called the Cosmic Treasure Chest, is composed of 1,100 stacked images from the telescope. Here there are stars and galaxies and a vast array of astronomical objects, many of which will never have been studied in detail before. When you explore Rubin's images, you could be among the first humans to ever see some of these fuzzy objects in the distant universe. The telescope has already discovered 2,104 previously unknown asteroids, and it will discover millions more new asteroids in just the first 2 years of its 10-year observing program. Once discovered, these asteroids are passed to the Minor Planet Center every day for follow-up observations. This ability to monitor changes in the images from night to night and over longer timescales is one of the strengths of the telescope. The observatory will essentially provide us with a 10-year ultra-high-resolution movie of a large part of the universe, which will discover supernovae, variable stars, asteroids, exoplanets, and probably many other currently unknown time-varying phenomena. This incredible first data release is just a small hint of the things Rubin will achieve during its 10-year observing run that will begin once the final checks on the instrument are complete. Head over to the observatory's main website to explore the details for yourself. I've included a couple of links in the description. That's today's video. I will see you in the next one. Another new exoplanet today, but this one is a first. It's the first exoplanet directly detected with JWST and a coronagraph on the MIRI instrument. Because of the bright starlight and because planets are dim and very close to their stars, at least from the perspective of observers on Earth, direct detection of exoplanets has so far proved very difficult. Enter the coronagraph, a device that blocks the light from a central star so astronomers can investigate the area around the star without the bright starlight overpowering everything else in the image. It effectively creates an eclipse of the star for the instrument. Our current theory of star and planet formation is that stars form from a rotating, collapsing cloud of gas and dust, and planets then form from a disk of material that surrounds the new star. The exact timing of this is not clear. We had always assumed the star formed first and then the planets later, but several new observations suggest that the star and planets actually form at almost the same time. In either case, it's much easier to try and find planets in disks of material that we are looking down on from the pole than systems we see edge on. Think about looking down on our solar system from above. It would be much easier to see the planets this way than if you were looking at the solar system edge on to the disk. The team that discovered the new planet used all this information to their advantage, focusing their search on young stars with planetary disks that were known to be oriented face-on to us based on previous observations with other observatories like the Hubble Space Telescope. As you can see in this image of the star, TWA7, there are 3 faint rings or gaps visible in the disk around the star, and astronomers assume that gaps like this indicate the presence of a planet. The difference here is that in the inner R1 ring, JWST has actually detected a source, and after a lot of checking and double-checking, the scientists have concluded the source is a planet roughly 30% the mass of Jupiter, orbiting about 52 astronomical units from the star. Relatively speaking, this is a very small planet to detect directly, and the researchers believe they can use this system to find planets with just 10% the mass of Jupiter in the future. Other, even more advanced coronagraphs are in development, and it'll be interesting to see how many more small exoplanets we'll be able to directly detect with those. The paper is published in the journal Nature Astronomy, and it is open access. I'll put a link in the description. That's today's video. I'll see you in the next one. We've talked a bit about ESA's biomass experiment before on this channel. This Earth-observing satellite was launched April 29th on a Vega C rocket and is currently in its commissioning phase. That's where the team checks that everything's working on the satellite, tests the science instruments, and fine-tunes the details ready for the main science mission. At the Living Planet Symposium on June the 23rd, ESA released the first jaw-dropping images from this testing phase, and we'll get to those in a second. The mission is the first P-band synthetic aperture radar to study the Earth from space, and its job is to measure the amount of woody biomass in the world's forests. Measuring this biomass, which is the total mass of trees minus the mass of the water in the trees, will give us an equivalent measurement for how much carbon is stored in the world's forests, and over the 5-year mission, whether this amount of carbon is increasing, decreasing, or remaining the same. This is crucial as we try to understand how effective forests are in helping combat the effects of climate change. The problem with trying to study biomass from space is that when you look at a forest from above, you just see this. What we're interested in is not all these leaves, but the woody biomass below. P-band radar has a wavelength of around 70 centimeters and was selected because it can penetrate the upper canopy layer of forests and actually measure the woody tree trunks and branches all the way down to the ground. For example, here's a biomass satellite image of a Bolivian rainforest. The green in the image is rainforest, the reds are floodplains, and the blue-purple is grassland, and the snaking black thing running through the image is the Beni River. Bolivia has suffered significant deforestation to make way for agricultural use. In addition to penetrating the forest canopy all the way to the ground, the other huge advantage the biomass mission brings is its ability to combine images from different satellite passes to gather information on forest height. By combining data from these passes, scientists can get a very accurate estimate of forest biomass from orbit. Here's another biomass image of northern Brazil showing wetlands below the dense forest canopy in pink and red. As you can see in this third image over Indonesia, biomass's ability to penetrate all the way to the ground means it's also useful for generating topographic maps of forested areas. It's going to be super interesting to see the data we get from biomass when it gets into its stride and starts science operations. That's today's video. Have an awesome weekend. I will see you back here on Monday.